Hi, hello students. Welcome back to India's most comprehensive online learning platform, Byjus Exam Prep. This is Anil Prasad Surampudi, and in this session, I'm going to give you a perspective towards this synchronization. Because why I chose this problem, why I chose this topic, I just need to admit initially. Most of the people I knew that find it very difficult to understand this topic. But let me assure you that this is one of the simplest topic. Being a computer science engineer, we just need to understand and provide a solution for the synchronization as simple as chewing a gum. So here what I'll do is, I'm going to give you a perspective to understand this synchronization problem. First of all, we need to understand, of course, that the total concept is all about producer-consumer. Here, in this session, we will discuss about what leads to the synchronization problem by using the well-versed, what we call the most famous problem, the classical synchronization problem, that is producer-consumer. And let me tell you something. I'm going to take you people into the concept from multiple dimensions. It is not like opening one gate will be able to enter into the topic. I will give you the different dimension where you will be able to watch this total problem and you will be able to perceive and understand it very, very easily. But I expect something from you people. That is, you just don't need to do anything. Just have a scribble pad, and if you find out an important point, just write it down. You don't need to even improvise, you don't need to get the information from your classroom or anything as such I need. Only the thing is, just listen to the class plainly, right after which you'll be able to understand each and every point of synchronization, that is producer-consumer, how we are going to enter into the concept of the synchronization through the producer-consumer. Okay, so let us start. Hi Chitra, very good evening. And let us mark your presence. Let me see. Fine. Good. So, shall we start? Okay. Let us enter into the world of producer-consumer problem. So, he's all about my experience. You all guys know about my experience and expertise. Now, let us get into the details. Let me tell you something. Let us not dive into the topic directly. For this, let me take the help of ancient days of the operating system. Let us think simple, very simple indeed, so that we will understand the concept from multiple dimensions as expected. Okay, so understand something. In the ancient days of our operating system, how it was designed, let us have a recall. The operating system was expected to have only one program to execute. For instance, I do have a main memory. This is my main memory. The good old friend for a computer science teacher, computer science student, or a application developer, or a programmer, what do you call? If you use a computer system, you know that the main memory, the significance of the existence of the main memory. Then we do have a CPU, right? What is the job of the CPU? CPU's job is to execute a program, simple. And where the programs are residing, the programs are expected to stay in main memory. In the earlier days, we do have only one program. The operating system is expected to execute only one program at a time. That is, only one program will get loaded here. Then, the moment a program gets loaded into the main memory, as it has got no competitor, hi Bharat Sharma, hi Anu, very good to see you people back in the live session. So, stay focused. I love this response, and okay. Have your wits and all your enthusiasm. Stay till the end of this class. I'm going to make it very, very simple indeed. Yeah, now let us understand. In the ancient days of the operating system, as I told you, an operating system was expected to execute only one program. That program will get into the main memory. Since there is no other program which is going to compete with this program, immediately, the moment it enters into the main memory, it will make its way to the CPU. So, CPU will execute this program. Let us name this program. I will use, see, in the entire session, I will use your names as references. So, this program is CHI. Okay, CHI .c, this program. Okay, this program has got, no competition whatsoever. So, this goes into the CPU. So the CPU has only one job to execute at this point of period. Now this chi.c is executing right now. What will happen? Sooner or later, this chi.c will go for an IO operation, right? This is purely because every process will switch in between two things during its entire life cycle. We are talking about programs, right? Yes or no? Now let us say there is a process. That process during its life cycle, it will execute initially in the CPU. Then it will go to perform an IO operation. Okay, this is called a CPU burst and IO burst. For instance, when you execute a program, your program may read a package. What is a package? Package will be retrieved from a file system which is there in the secondary memory. Or else when you program, execute a printf statement. Printf statement, when it is executed, the console, the screen must respond. For that, the program which is executing in the CPU needs to wait for this IO device to respond. Once after the IO operation has been finished, the same program will come back to the CPU. Then it will go to one more IO operation, come back to the CPU, goes to IO operation, come back to the CPU. This is the total life cycle of a program. I'm pretty much fine and great, Anu. How you guys are? Yeah. So now this is the scenario with any program or a process. In the operating system, we'll call any program as a process since a process is a program in the execution. I'm not getting into the simplest details. When you run a program in the main memory, that program will be considered and named it as a process. So this process, when chi.c, the moment it enters into the CPU, it will switch in front and forth in between CPU and IO devices. So CPU will execute within the CPU for some time, right after which it goes to the IO device, then it comes back to the CPU, goes to another IO device. So it will move in and out of the CPU. Here the problem is, I will tell you, this is the biggest problem for the CPU. Because the CPU is expected and considered to be the important resource for an operating system which should never get wasted. But imagine when chi.c goes to an IO device, obviously the CPU is kept idle. And the CPU will be idle in a single programming operating system until and unless this process comes back and execute within the CPU for one more time. Okay? Now, in order to utilize the CPU productively, what the designers suggested and proposed is a multi-programming operating system. Because in the single programming operating system, we are not able to utilize the CPU productively. When a process goes to the IO operation, obviously CPU would wait and kept idle. Keeping the CPU idle is the biggest crime from the designer's perspective. We can never keep the CPU idle, right? So CPU idle meaning throughput will get decreased, simple. So right then what happens is, hi Abby Developers, how are you? Very good to see you people back. Yeah, now we propose, rather, the designers proposed a multi-programming operating system. What is a multi-programming operating system? At any point of period, main memory will be loaded with many programs, not a single program. In a multi-program, in addition to chi.c, what are the other people I do got? anu.java, maybe C again. And there is Bharat, BHA. These guys also are the programs that are waiting in the main memory. Now understand. What will happen at this point is, there is no process can directly enter into the CPU. Earlier we had only one process that can directly enter into the CPU, but we have a competition in between the process. Since there are many processes in the main, it's not a single process. There can be n number of processes that can be kept in the main memory for execution. The moment a process arrives into the main memory, that is considered to be in a ready state and a ready queue. What is ready queue? When I go to the main memory, that means that I'm ready for execution. Sooner or later, operating system should pick me up and send to the CPU. The moment I get into the CPU, I will start my execution. But here, the problem is I'm not the only guy residing within the main memory. There are other competitors. I have Anu is with me, Bharat with me, and Chitra is also with me. There are other people who are watching. Also, let us say all of you guys are processes. Here, how would I be scheduled? How would I be getting into the CPU? In what way I can make my way into the CPU? For that, what we need to do is, being an operating system developer, we need to have a guy. This guy will use an intermediate guy who can order these processes. This guy, I will call it as a scheduler. Okay? This guy is a scheduler. Scheduler also is a process, mind you. This guy is also a process. But this guy's main job is, whenever he executes, he will find out which is the next job that can come and occupy the CPU. But on what basis the scheduler works? Does scheduler know who is BHA.C? What is this program? Does scheduler know what is CHA.C? Does scheduler know what is ANU.C? No, scheduler doesn't know what is that code all about. Scheduler knows only one thing. And the parameter that he's working, let us say the scheduler is based on SJF. If it is SJF, he will find out the shortest job and send it into CPU. And he will find out what do you call, if it is a preemptive scheduling or what do you call the interruptive scheduling, what he will do is, based on some parameters, he is going to select the next job or the next process that can enter into the CPU based on some priorities. And at the same time, understand, keep it in your brain that if I am the scheduler, you guys, all the process, I don't know who are you. I don't know what is your code. I don't know what are the different modules that you have. My job is pretty much simple. I will look at the scheduling algorithm, on what basis I'm working. Priorities. There are several parameters on which the priorities can be decided. I will analyze all of your priorities. I will pick up the right guy, which has got the highest priority. I will send you guys into the CPU. This is my job. Okay, keep it aside. This scheduler has got no idea what is the code within the process. Keep it in your brain. This is all required. I'm going to retry all these things the moment we start synchronization. Okay, you keep it aside. The next thing that I'm going to introduce here is, how many processes we do have right now? Many processes, right? It's not a single process. Now the operating system, there are several objectives it has to meet. What are the objectives? One of the main fundamental objective for any operating system is the response time. What is the response time? Every process is expected to, be executed at least for a while. You don't need to completely execute it. Being an operating system, you don't need to execute all the process completely. But at least a portion of the program, if you're able to execute, then that means that the program is getting a proper response. So what operating system does is, again, I do have CHI.C or BHA.C and Java or whatever. Maybe ANU, maybe it's a movie. I will say M, ANI, it is myself. Let us say I'm a file. Anything is a program. Now, let us say there are many programs which are in the main memory. In order to achieve the reasonable response time, what operating system does is, operating system will talk about concurrency. Concurrency meaning, any ideas what is concurrency? Shortest jobs, excuse me. Any ideas about the concurrency and preemption? Concurrency meaning, I will tell you. Let us say this CHI.C is a program which, all of these programs. Initially, ANU.M has been scheduled into the CPU. But operating system will not allow ANU.M to execute completely. Within no time, it will preempt ANU.M out of the CPU. Immediately, one more process it will allow to enter into the CPU. These switches will occur so rapid, such that the user will get a feeling that all the programs are getting executed concurrently and parallelly. Understand carefully, these programs are not executing in parallel. If you do have a single CPU, one CPU at max can execute only one process at a time. If any CPU boasts that I will execute too many processes, despite being a single CPU, you don't trust, you don't believe. If you do have one CPU, no matter what, it will execute only one process at a time. That's it. You won't be able to execute too many processes. So, when being a simple CPU, it will execute only one process at a time. Right? So, operating system, in order to give an illusion to the user, in such a way that all the programs are executing parallelly, it will switch in between the programs very rapidly. For an instance, Anu M got scheduled immediately within no time after executing one or two lines of instructions. It got preempted. And CHI.C entered. Again it got preempted. BHA.C entered. Again it got preempted. Finally, the poor guy, ANI.C entered, and he also got preempted. So, in such a way, operating system makes these switches happen so rapidly that the user will get an illusion all the programs are executing simultaneously, but it is not simultaneous execution, it is concurrency. Okay, so keep these things in your mind. So in the first slide, what have we discussed? In this first slide, I just want to remember only 3 points. Okay, let me admit what are those. The first one is scheduler. What we expect from a scheduler. Scheduler is a simple guy who can schedule the next process. He doesn't know about who is the process. He doesn't know about what is the code within the process. He knows only about there is a parameter on scheduling. There is a priority on scheduling. According to the priorities, he'll work out and will pick out the next guy. That is because there are too many processes. Second one is concurrency. What is concurrency? In order to give an illusion to the user, operating system executes all the process concurrently, switching in between process very rapidly. I am sent into the system without finishing. I got preempted. I got pulled back and sent to the main memory. Even if I like or don't like, that doesn't matter. In order to achieve greater concurrency, what do you call the greater throughput and illusion to the user that all the programs are responding and executing parallelly, concurrency needed to be achieved by the operating system. And the third one is preemption. So in order to have this concurrency happen, operating system also should follow preemption. What is preemption? Pulling out a process from execution and putting it back to the main memory is called preemption. Okay? Let me tell you, despite concurrency in the preemption improves the system performance, but for an operating system, it is the most heart attack problem. The moment operating system has to implement these two, concurrency and preemption, it will hold its heart or its head, saying that I need to go through a lot of difficulties in order to maintain this concurrency and preemption. Since lot of problems are going to arise where I have to solve. I need to follow many of the algorithms. I need to resolve many things here. So this concurrency and preemption are going to put the operating system in n number of troubles. How, what, why? We're going to see right now. This is where exactly we're going to start the concept of the synchronization. Oh, no, it's not needed. It's not needed. Context switching between a faster manner. Yeah. Programming running at the same time. Very good. Now, let us stay focused. Let us start opening the door of the synchronization, or something which is called a cooperative process. What is a cooperative process? Understand carefully. Again, let me draw the block diagram of the main memory. This side I will draw this side this time. This is the main memory. Okay. Let us say there is a process P1. Let us say AB. This process enters. The moment the process enters into the system, this process enters most of the times as an independent process. What is an independent process? In every time when a process enters into the system, it needs a certain set of resources. It requires CPU time for execution, main memory space to reside, file system to read and write, and I/O devices for having the execution done by the user. All are required by any program that comes into the computer system. But understand, any program, most of the programs will enter into the system as an independent process. That means that any of these resources you assign, but those must be assigned to the specific process exclusively. That is, if a resource has been assigned to this AB program, the same resource cannot be allotted to any other program at all. So this is a requirement for an independent process. When I enter, memory space should be exclusively for myself. CPU time, when I enter into the CPU time, I should use my CPU's portion. Next thing is when I use a file system, the moment a file is allotted to me, either for reading or writing, that is exclusive. And I/O device, when I'm accessing one I/O device such as printer, at that point, at that instance, only myself should be able to access the printer or any I/O device. This is an independent process. But understand, life is not all simple. all this simple. Understand that there is Chitra started developing an application. Chitra started developing an application. Meanwhile, Abhi de Villiers also started developing her application, of course, his application. Who is an application program developer? Let us say you're designing an application. For instance, word processing application or a media player application. Earlier, tomorrow, what you're going to do? Tomorrow, maybe in the upcoming, right after you finish your graduation, you're going to look at yourself most of the times as an application developer. Kernel developer, let me tell you, there are many ways to get into the software field. One is kernel developer. Second one is application programmer. If you want to become an application programmer, your life will become very simple because our job is fairly simple. We don't need to, construct bigger modules of the code. We need to design the application based on an API. I'm not talking about APIs or anything. When it comes to the kernel developer, things are very different. Kernel developers needs to design even the APIs. So kernel developers' life is very complicated, but application programmers' life is very simple. Now let us talk about an application programmer. Abhi de Villiers started its application. Let us say media player application. Application is a collection of processes, right? Of course, this is a simple thing that is expected out of every application. Open MS Word. MS Word is a collection of several processes. Some process, most of the process, 90% of the processes within any application are independent. But some processes are cooperative, are dependent. What is a cooperative process? When it comes to the cooperative process, a process wants to communicate with the other process. Let us say there are 100 processes, P100. All these processes will make up your application. Out of which, there are 20 processes or cooperative process. All the remaining 80 processes are independent. All the resources are exclusive. But these 20 processes, let us say, want to communicate with the other processes. They will admit the moment they come into the computer system, the moment they come into the main memory, they will admit the operating system that we are cooperative. We want to communicate with each other. Then the operating system again holds its head. Because this is where exactly the problem starts. Okay, so somehow or the other, either the operating system does like or doesn't, it needs to establish a communication among these processes which would like to communicate with each other. Okay, now there are two ways to establish the communication. One is shared memory and one more is message passing. Our concept is all about shared memory. Message passing is the simplest technique. I don't want to explain message passing. Message passing is anybody's game. Simply you can go through the books and within one page total message passing can be completely covered. But let us discuss about the shared memory, which throws a lot of complexities, a lot of challenges. We are going to make the shared memory concept very simple. Okay, let us enter into producer consumer. Okay, so let us call independent process cannot affect or be affected by the execution of the another process, since an independent process will be given with an exclusive set of resources which can never be shared by any other process. Okay, and the next thing is cooperative process can affect or be affected by the execution of another process. Since let us say I'm a process. During my execution, I want to communicate with one more process, ABD. When I make it, of course, ABD can affect myself or I can affect that process during the execution. You can ask me, sir, what is the need? You can execute as an independent process itself, right? It cannot happen. I will tell you. For an instance, I will give you a wonderful example. Compiler and loader. I hope these words make sense, right? I don't need to explain what is a compiler, what is a loader. Compiler is a compiler, loader is a loader. Compiler is required to compile a program, after which some data will get generated as an output of the compiler. Then what exactly is going to happen is, the loader is going to use the output which is produced by the compiler. Loader cannot execute unless the compiler has already finished. You got the point? So compiler and loader are the cooperative process. They have to execute in a sequence of order, and the data that is produced by the compiler will be in tandem used by the loader. I hope you got it completely. Some process, unless they communicate with each other, they won't execute. Simple. So, advantage of process cooperation is you can go on listing any number of things, any number of advantage. You can talk about information sharing, computation speed up, modularity and convenience. But let me tell you, These doesn't sound good to the operating system. Since operating system will need to find out some solutions to the complexities and difficulties that are arised by the difficulties that are thrown by this cooperative process. Let us talk about a producer-consumer. Okay, straight away. Paradigm for cooperative process: producer process produce information that is consumed by the consumer process. I am a producer, one of you guys. Who is this who are watching? Let us say, respond. Say hi. Already I used you people. Fine. I will say ABD again. ABD is consumer. I am a producer, ABD is a consumer. Understand carefully who we guys are. I am a process. Producer, I'm a producer, ABD is the consumer. Got me? When I got scheduled, I will produce. When he got scheduled, he will consume. For that, what we need to do is, we need to have a common shared memory. So, let us understand. In this common shared memory, let us say we talk about a buffer. Total size of the buffer is 0, 1, 2, 3, 4. Understand, I'm a process. When I execute, when I get scheduled by the scheduler, I will get into the CPU. When I execute, one item will be added to the buffer, item 1. When he gets scheduled, he will be able to retrieve an element, rather read an element, remove an element from the buffer after reading it. But understand, we guys are primarily our processes. And who is scheduling us? Guys, participate. I'm not talking about the messages. I'm not talking about the message passing. Let us understand this very carefully. Who is scheduling us? There is a scheduler is there to schedule us. The scheduler doesn't know who is the producer, who is the consumer. The scheduler, of course, as we will give the scheduling to somebody. Okay, fine. There is some guy called X. He is the scheduler guy. And he schedules based on some priorities. At the same time, he doesn't know who is the producer, who is the consumer. Based on some priorities, he can either schedule consumer or schedule producer. But producer and consumer, they need to execute in a specific order. Otherwise, it doesn't work. When the consumer gets scheduled initially, prior to the producer produces any more element, any item in the buffer, consumer cannot execute. If he executes, he's going to read a garbage value. Making sense? I hope it makes sense. Let us say there is a consumer. Producer hasn't been scheduled yet. Our X, who is a scheduler, schedules consumer prior to the producer. When consumer enters, there is no item that can be read. But still, when his code executes, he will read the first element before it gets produced. What will happen? He is going to read a garbage value, right? Is it making sense or not? I hope so. Now, this is the problem. So, since from the operating system there is no guarantee that producer and consumer will be executed in a specific order, we need to make sure that additional modules are written within the producer and consumer in such a way that they will execute in a specific order without having any chaos whatsoever. Okay, so now let us define this producer-consumer problem perfectly. Now, let us see. I will tell you what is the problem with the producer, what is the problem with the consumer, why we will call producer and consumer as a problem. If the consumer gets scheduled prior to the producer produces any element, consumer consumes a garbage value, as I just stated just a short while ago. Producer, let us see, the same guy X, who is this X? He is a scheduler. He did not schedule the consumer at all. He keep on scheduling the producer. Every time when he gets into the CPU and executes, producer will add one item, okay? And again, the total size of the buffer is, let us say 5, 0, 1, 2, 3, 4. Every time when he executes, he will add an item to the buffer. Item 1 is added and the producer went off from the CPU. Then again, this X decided to schedule producer only, depending on some priorities. Of course, producer will come back, will add one more item, will leave. Again he got scheduled, will come back, executes, and add one more item into the buffer, leaves. Again, when he gets scheduled, will add item 4, leaves. Item 5, leaves. Got me? Now what will happen? If the scheduler decides to schedule producer for one more time, he is going to overwrite one of the element which has already been written but not yet consumed by the consumer. Once again, what is the problem with the producer? Producer, if he keep on getting scheduled, sooner or later, buffer will completely be full. Right after the buffer is completely full, if the buffer is, there is no end of the buffer, obviously producer can add any number of elements, but we need to be practical. It cannot be infinite buffer. It has to be finite buffer where the chunks are pretty much limited. So if a producer keep on getting scheduled, obviously sooner or later buffer will completely be full. Right after it is completely full, even if he gets scheduled for one more time prior to the consumer consumes at least one item, he is going to overwrite an element, right? Because simply a code when gets executed, one item will be added no matter what, either it's been consumed or not, whether there is an empty chunk or not, whether there is an empty location to produce or not, nothing will be considered. Whenever producer comes, he will add the element. So these are the problems with the producer and consumer. So we need to make sure that there has to be a constraint imposed on producer and consumer in such a way that even if the consumer gets scheduled before the producer, he should not be able to consume any item. Even if the producer gets scheduled right after buffer is completely full, he should not be able to produce any more item. So this constraint must be imposed into the modules of the producer and consumer. Understand? Scheduling is done by not producer, neither by the producer nor by the consumer. It is done by the third guy. He don't know who is the producer, who is the consumer. That is his wish. I mean, if he says, Mr. Producer, you get into CPU, he will have to get into the CPU. If he says you come out, he will have to come out. Because scheduler works on some parameters, some priorities. Okay, so producer and consumer need to be provided with some additional modules of code in which the constraints are imposed. Okay, did I make it myself clear? Hi Santoshi, hi Utkarsh Kumar. Full operating system practice for GATE and university. You don't need, just follow the sessions carefully. Just follow my sessions. I'm going to, cover entire operating system throughout this. Initially at this, I'm explaining what you call synchronization, right after which I'm going to come with many more topics. So any doubts so far? I hope there are no doubts. So let us go ahead. Okay. Bounded buffer assumes that there is a fixed buffer size. There is no unbounded buffer. That means that can the buffer size be unlimited? Never. Buffer size will also be limited, will always be limited. Even if you allot a total main memory size to the buffer, still it is limited. So producer will have a problem. If the buffer is completely full, he should not produce any more item. Consumer will have a problem. If the buffer is completely empty and he got scheduled, he should not consume any element since he is going to get a garbage value, right? Now, so what we do is, in order to stitch this producer and consumer, synchronize them properly for an orderly execution, we are going to add some additional modules of code in such a way that producer won't produce, producer will be under his constraint as I told you, consumer will also execute under the constraints. So here the thing is, I'm going to define a buffer size. But let us say, in order to make it simple, I will assume that the buffer size just is equal to 5. And then I'm going to define a structure. I hope this makes sense. It is the definition of a structure, right? Inside the structure, I will use two logical pointers. One is in and one more is out. Once again, initially I need to define a buffer size in which, buffer size is just equal to 5. I will interpret as 5. And then I'm going to define a structure with a name item. What is the structure name? I named the structure as an item. In this structure item, I defined two integers. One is in and one more is out. Both are initialized to 0. Okay, but what are these in and out? These in and out are the logical pointers to the locations of the buffer. How it exactly does work? Follow this carefully, you're going to understand it very, very precisely. Yeah. Let us understand how exactly it does work. Let us say the producer want to enter. The producer is being scheduled. What is the restriction or the constraint to be imposed on the producer? Producer, if he keep on getting scheduled, he should not be able to produce right after the buffer is completely full, right? So 0, 1, 2, 3, 4. Now what exactly would happen is, initially, when the producer when enters into this, before the production happens, I will tell you, he will wait on one condition. That is, he will check with the while condition. If the while condition satisfies, then that means that he won't be allowed to produce. What is this while condition? N plus 1 mod buffer size equal to out. This is the while condition which restricts the producer from producing any more item. How exactly it does work? Understand carefully. Initially, you know that in equal to out equal to 0, right? So when the producer gets scheduled initially, what will happen? In is equal to, I am waiting on a condition n plus 1 mod buffer size, I will say BS, equal to out. If this condition satisfies, you can see there is a semicolon, will keep the producer inside the while loop all the time. He will be caught up in the infinite while loop. N plus 1 mod buffer size equal to out. What is in? In is initially equal to 0. Plus 1 mod buffer size. What is buffer size? Buffer size is equal to 5. Equal to what is out? 0. This condition fails since 1 mod 5 is equal to 1 but not equal to 0. So the producer will be able to come out of this while loop and he will be able to produce the next element. Where the next element is going to get produced? The next element is getting produced at buffer in the buffer where in is pointing. You understand this? Next to produced is just nothing but an element. The element will be added to the buffer exactly at the position where in is pointing in the buffer array. Where in is pointing, in is pointing at 0. So I would say item 1 will get added here. Right after item 1 has been added to the buffer, in is getting incremented. In is equal to in plus 1 mod buffer size. In plus 1 mod buffer size will have the in updated in a circular array. So the moment it goes to 4, one more time if it gets updated, it will come back to 0. Right? I know that, I hope that you know about this constraint. So next what will happen? In will become 1 because right after the production happens, in will become 1. So let us say producer has got scheduled for one more time. When he got scheduled for one more time, what exactly will happen? Again this condition fails. In plus 1 mod buffer size. What is in? In is equal to 1 right now. 1 plus 1 mod buffer size is equal to 2 but not equal to 0. Out is equal to 0, right? So he will be able to produce one more item where in is pointing. Where is in right now? In is exactly at 1. So item 2 will get added. Right after addition of the item to the buffer, in will get incremented. In will become 2. Then obviously here also one more item will get added since condition fails. Item 3 will get added, right after which in will be equal to 3. Now again even if you check the condition, in is equal to 3 plus 1 mod buffer mod 5 is equal to 4 but not equal to 0. So he will be able to produce one more item. Item 4 will get added into the buffer, 4 will get added into the buffer, right after which finally in will come to 4. Now understand, you can clearly understand that the producer will be caught in a while loop if he get scheduled even for one more time. It is simply because the condition is getting satisfied. How the condition is exactly getting satisfied? Where in is right now? In is equal to 4, right? In plus 1, let me write again, in plus 1 mod buffer size equal to out. In is equal to 4 right now, plus 1 mod buffer size is equal to 5, equal to 0. Of course, 5 mod 5 is equal to 0, and the condition satisfies, and the producer will be caught at the infinite while loop. Did I make it myself very clear? Yes or no? Yes or no? You got my points? Arey, you people taking too much time to respond, or is it the system responding slow, or you people responding slow? Make it, be active, electrify. Just, I mean, we need to be, very active indeed. We need to make the other people active. Our shoulder should never drop. We always should, keep. I know that it is the time where we about to sleep, but as long as we stay awake, we should be as active as any part of the day, any other part of the day. So, respond. Yes or no? Everybody, very good. Where are you, Anu? Where are the other people? Utkarsh. Yeah. Now let us say the producer won't be able to produce any more element. Constraint has been satisfied. The producer won't be able to produce any more element. But here, there is one loophole, one slightest loophole here. What is the loophole? Producer will just be able to add, with this module if we implement, producer will just be able to add the total number of elements which are just equal to buffer size minus 1. He won't be able to add any more item more than buffer size minus 1 elements. If the buffer size is equal to 5, he will only be able to add 4 elements, but not 5 the fifth element. If at all, the producer has to produce one more element at this point, this out should not be at 0. If out goes to 1 or 2 after consumption, then the producer will be able to produce the next element. I will show you when out will get updated. Okay. Now, so far producer, well and good, everything works fine, except a small disadvantage. We can take it since we stitch the producer and consumer in a proper order. They are executing in a proper order. Now let us see the consumer module. The consumer module is fairly simple. If both in and out are equal, the consumer won't be able to consume any more element. What is in and out? In equal to out equal to 0. That means that there is no element in the buffer, neither is added nor retrieved at this point initially. Okay, hold on. Let us get into more detail. It is not, I need to take you people into the multiple dimensions. I can't leave you people understanding a simple point and keep it into your brain. Let me take you to other dimension where in and out both can be 0. For an instance, there are 2 elements. Item 1, item 2. It is 0, it is 1. Now you can see that in will be equal to 3 after the production, and out will be still is at 0 because out is not updated at all. Out is still equal to 0. Let us say consumer comes. In equals to out. When in is equal to out, he will wait. Since you can see the semicolon, although it is in the next slide, the next line, semicolon will restrict the consumer from consuming. But here the thing is, in is not equal to out. In is equal to 3, out is equal to 0. Consumer will be able to enter, will be able to consume the element from the buffer. Okay. So where exactly he will be able to consume? From the buffer, where out is pointing, he will collect the element and will get it transferred to next consumer. Get it? So then what will happen? Out will get incremented. Got it? Then out will become equal to 1. Out will be equal to 1. Then he can get scheduled for one more time. When he reads one more element, what will happen? Out will be incremented for one more time. At that time, out will become 3. This is 1. In equal to 3 equal to out. So there are 2 things. When in and out both are equal to, when both in and out will be equal, in and out both are equal, even before no item has been produced, or the items that are produced by the producer have already been consumed by the consumer. In both cases, in will be equal to out, right? Initially, in is equal to, out is equal to 0. That means that no items have been added by the producer. Let us say producer added 3 elements, consumer consumed 3 elements. At that time, in will become out, right? So these two will be equal in two cases. In two cases, let us say the consumer should not consume any more element. So this is the constraint that is imposed by the consumer. So this is one solution to stitch the producer and consumer problem to execute in an orderly fashion. But the problem is, as in the previous slide, buffer size is not completely being utilized at all. This solution is perfect, but with the slightest disadvantage. What is the disadvantage? If the producer keep on getting scheduled, he won't be able to produce any more element than buffer size -1 elements. I hope you got the point. Since there is a loophole in this code, we can't do anything with the code. So what we need to do is we need to follow a better approach. I told you for several times in my previous session, can we afford losing even a single chunk in the main memory? I told you for several times, can we lose at least a single chunk in the main memory? Where is buffer? Buffer is in main memory. And that we, producer and consumer, procured space from the main memory. Can we afford losing even a single element? Yes, son, tell me. Santoshi or Anu or anybody who is Bharat, who is listening to the class. Tell me, can we lose even a single element that is given? I am given a memory space. What memory expects? Memory expects. What do you mean by busy waiting? I will come to you. Busy waiting I am not explaining right now. Busy waiting meaning, I will come there. So let us get into the topics very slowly. Busy waiting is not a big deal. I will tell you, but not right now. Okay? Yep. We can't afford losing a single chunk of memory. So what we need to do is, I need to refine this to one practical solution in which the producer, even if we get scheduled continuously before the consumer consumes any element, he should be able to produce the number of elements equal to the buffer size. So what I'll do is, see, a shared memory, as I told you, shared memory is one method in which two processes can communicate. Operating system will create a shared region. In this shared region, both producer and consumer should be, any process, not only producer and consumer, if there are 20 or 30 or n number of processes which want to communicate with each other, among them, there will be a shared memory region. I would say SR. This shared region will be utilized. Okay, so an area of the memory shared among the process that wish to communicate major issues to provide a mechanism that will allow the user process to synchronize their actions. Already I have discussed this. Let me add one feasible solution to the producer-consumer problem to avoid the previous disadvantage that we got. What is that? Buffer size is not being utilized productively. So what I'll do is, I will use one more variable which is called counter. Stay focused right from here at this point. I want to take you people into the world of synchronization. This is exactly the origin of synchronization. I am using what is called a counter variable and initializing it to 0. Understand, this counter is a shared variable which is going to be used by both producer and consumer. Okay, so what will happen is, of course, we are still using in and out logical pointers. We are not, avoiding logical pointers. We are still using in and out, but in addition to which, we are also using counter. Counter is a simple variable, and it is not being updated in a circular fashion. Counter is a variable is being updated directly. Counter plus plus. Understand the difference between in is equal to in plus 1 percentile buffer size and counter plus plus. The difference in between these two is just simply in will rotate back. How? Should I explain you that also? Fine. Okay, I will do it. 0, 1, 2, 3, 4. Let us say in is at 4. One more time if it is incremented, in will become 0 because 4 plus 1 mod buffer size is equal to 0. So in will come back to 0. But counter plus plus, there is no practical restriction on the value that counter can take because it can simply increment it, right? So understand carefully. So the producer when gets scheduled, he will check only one thing. Is the counter equal to buffer size? Initially, counter is equal to 0. Is it making sense or not? Initially, Yeah, I mean, do not enter. Hi sir, hi Sachinarayana sir. Let us understand, counter is equal to 0. Counter equal to 0, obviously the condition fails. Counter is equal to 0, buffer size is equal to 5. As the condition fails, the producer will be able to produce the next element that is going to be produced at the in the buffer where in is pointing. Where in is pointing? In is pointing at 0. In and out, mind you, are the logical pointers to the locations of the buffer. Initially, both in and out are equal to 0, needless to say. Okay, so right after the production happens, in will increment. In will be equal to 1. Counter will also be equal to 1. Alright? Then one more item gets produced. This is item 1. Right after which, item 2 gets produced. When item 2 gets produced, in will become 2. Counter will also become 2. Then one more item can be produced. Item 3, because condition is being failed, right? As long as the counter is not equal to the buffer size, producer, no matter for how many times he gets scheduled prior to the consumer, he will add one element into the buffer every time he gets into the CPU. So item 3 get produced, right after which in will become 3 and counter will become 3. Then item 4 here, okay, and then followed by in is equal to 4 and counter will be equal to 4. Now in the previous case, we won't be able to produce any more element at this point since we checked with a different condition. But since right now, as the counter value is not equal to the buffer size at, the producer will be able to produce one more element here, that is item 5. I hope it makes every sense right now. Right after the 5th element and 5th item has been produced, counter becomes 5, in will come back to 0. In will come back to 0. Then producer won't be able to produce any more elements since counter already made it to 5. Right? Now, producer will be caught up at the infinite while loop. Okay. Now, without wasting much time, I hope you got the point, right? Hi Nisha. Hi Nisha, any doubt so far? Yeah. Now understand, consumer is executing. Consumer life is pretty simple. Consumer needs to wait. Counter equals to 0. On counter equals to 0, only consumer will wait. When the counter is equal to 0, obviously it means that the buffer is completely empty. He won't be able to consume any element. If he is allowed, he is going to read a garbage value. So it is not allowed. This is the very reason why the consumer is going to wait on counter is equal to 0. When the counter is equal to 0, that means that there is no item added to the buffer, right? So the counter will be equal to 0. Understand carefully. My question is, can we still use in plus 1 mod buffer size equal to out? We can't use this at all. Even now we can't use in plus 1 mod buffer size is equal to out. Rather, I would, I'm talking about a consumer, right? In the earlier case, we used a different condition for the producer, that is counter equal to the buffer size. Now consumer, can we use both in equal to out? No. In and out will be equal in 2 cases. That is, right after the complete production, it will come back to 0, right? Even before any item is produced, think carefully and sensibly. Even before any item has been produced, right, in will be equal to 0. Right after the total production has happened, in will still become 0 because it's a circular array. So we can't use this. Okay, so I'm not hanging around here. I just want to get into this very quickly. Now, as the condition fails, he will be able to getting into this code. He is going to consume an element from the buffer from where out is pointing, and he's going to retrieve it to the next consumed, right after which he's going to increment out as well as he's going to decrement counter. Here the thing is, I don't need to talk much about the consumer. Here I just need to talk about counter and how it is being updated. Stay focused. What is counter? Counter is a shared variable. understand carefully something which is very important at this point of period to conceive and to be injected. Every time when you want to update a memory location, it's a variable. Variable is a memory location, right? It can never be updated at the memory level. First of all, every variable should be brought into the CPU. Within the CPU, there has to be a CPU register assigned to it, right after which any updation should happen. For an instance, I want to perform A++. What is A? A is a memory location. I can never update A at the memory location level. First of all, there has to be a process register to which A will get assigned. Right after this assignment happens, any updation should only happen on this process register. Then you increment R1. Finally, reflect the value back to the variable. I hope you got. Similarly, even here, what is the counter? Counter is essentially a memory location. The memory location, when it is being updated being a variable, it must be assigned to a processor's register. So the thing is, understand carefully. When the counter plus plus is being executed, there will be 3 equivalent machine operations should be performed within the system. Counter plus plus will have to perform 3 operations within the system. Each of these operations will require a machine language instruction to execute. The first instruction is an assignment instruction, where the counter will get assigned to one of the processor's register. In this case, I am talking about a producer only. Producer is making the counter value incremented. Consumer making the counter value decremented. So register 1 plus 1, right after assignment happens, increment should only happen, updation should only happen to the register. Right after the updation happens, this value of the register should be reflected back to the counter. Similarly, when you talk about the counter, minus minus, which is going to be performed by the consumer, similarly, this counter value, whenever the consumer is executing, counter minus minus will be assigned to a local register within a consumer module. Right after which, all the updation should only be performed onto the local register. Then, finally, the value of the updated, that is, the value of the register should be transferred to the actual memory location counter. Sir, since the count is a shared variable, what happens? The process gets preempted in between. Yeah, I'm just see, that is, superseding is not allowed. I urge you people to follow the step-by-step procedure. You take the things as they come. I will explain you exactly. I'm going to cover every option, every possible point here. But the thing is, let us go slowly. We do not dive into the topics ahead. We are simple. Our life is very simple if we make it simple. Don't make it complicated. Of course, I know that you people already had some idea about this, but keep your horses in hold. Okay, I will explain you. Exactly, that is what we are going to discuss as a subsequent thing. The thing is, as these are expected to be the instructions, what may happen? I told you already, there is a scheduler. Scheduler may not allow this counter plus plus to completely execute. Same time, the same scheduler may not allow the counter minus minus to completely execute. Scheduler is a simple guy. Scheduler don't know who is the producer, who is the consumer, which is the shared variable, what is being shared. Now let us say counter value. Within the next slide, I'm going to explain. Because the execution interleaving with counter is equal to 5. Counter value is equal to 5. Let us say he took the buffer size as 10. Total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let us say there are 10 elements in the buffer. Now let us say counter value is equal to 5. That means that 0, 1, 2, 3, 4. There are 5 elements in the buffer. And the counter is equal to 5. Now what happens? Producer executes and the consumer executes concurrently. What is concurrency? I am the producer, you are the consumer. Understand? I am executing. When I enter, I want to update counter. I executed counter plus plus. Counter plus plus has 3 machine language instructions to execute. These 2. Right after I execute these 2, for God's sake, I got preempted. For heaven's sake, you entered. What is his name? Mr. Tahir, you enter into, you are a consumer. You enter into the system and you're also executing concurrently at the same point the counter minus minus. It may not happen, regularly, but at some point of period, it may happen. There's a chance, there's a possibility, there's a probability that the producer and consumer executing at same counter plus plus, counter minus minus concurrently. But none of the process are allowed to complete its instruction execution. So at this point, I got preempted. Initially, I read the counter is equal to 5. 5 has been transferred to the register 1. And then register 1 has been updated to 6. But before I reflect the register value into the counter, I got preempted. And at the same time, Mr. Consumer entered. Consumer has to execute counter minus minus. But what he will read? Counter hasn't been updated. Let us understand. This is counter. Counter is 5, which has been read by the producer. Producer failed to update the counter since he got preempted. Within his local registers, the actual value of the counter was present. But actual location of the counter doesn't have the updated version, the updated value. So what this poor guy, the consumer, will read? This consumer is going to read the previous value of the counter, which is just 5. So obviously, the counter value he interprets as 5, he will transfer it to the register. System will make an assignment. Every time when a memory location is being updated, a variable is being updated, a process register must be allotted. So on the same ground, register 2 has been allocated, then has been decremented. Now let me tell you. Producer thinks that the counter value is equal to what? 6. Consumer thinks that the counter value is equal to 4. Register 2 value is equal to 4 right now. But right after counter value is equal to 5, one addition happens and one removal has happened. The counter value should just be equal to 5, right? This is the problem. What exactly is happening is the heart-thumping problem to the CPU and operating system. A variable is being updated very wrong. Variable is being updated inconsistently and incorrectly. This is the heart-thumping problem for an operating system. Let me admit precisely. After all, the computer system is serving the users only for the program execution, not for anything else. The program execution can never be put at stake. You can't afford a program execution. You can't afford something else at the cost of the program execution. You can't achieve concurrency. You can't achieve throughput. Talk about all those things right after you make your program execution correct. Got the point? So this is the problem that we are facing here. Now consider the execution. Register 1, producer execute register 1. Okay, right after, the same thing I explained here is given. Then consumer has got, producer executed first 2 statements. Right at the counter is equal to 5. So for the producer within the local registers, the value is equal to 6, but not updated. When the consumer executes, within these local variables, the value is equal to 4, but not updated. Okay. The final value of the counter depends on who executed finally. If the producer executes finally, the value will be 6. If the consumer executes finally, the value will be 4, but not correct. Nothing is correct. None of it is correct, right? So this is what the producer-consumer problem. I hope you got it completely right. Inconsistent result. Tahir, yes or no? There's no sorry. You just don't need to be. Yeah. Next, yeah. Value is not correct, simple. We have come to a solution which is not correct, which is not proper. This is what going to happen if you don't take the right approaches to protect the shared region access. Shared region access must be protected. Here the thing is, we should be able to define the origin for this problem. Here, simple. Either for you or for me, what we need to make sure, that the shared variable should always be updated correct. In this case, shared variable is a single variable. But in several other cases, shared region is a huge region. Let us say there are how many people? Let's say 13 people. All of you people are processed along with me. There are 14 processes. All of you guys, as we are cooperative process, we may share one table, one big table, or a database, or anything, a data structure. Every time when we access a shared region of the main memory, we need to make sure that shared region is accessed properly and correctly. Okay, so we need to define the origins of the problem. We already understood what is the problem. Shared region is being modified inconsistently and incorrectly. We need to avoid that. In order to avoid that, we need to provide a solution. But what happens when you directly go to the doctor? Will you be getting the medication? No. If you say I got fever, immediately no doctor is going to provide the medication. Why you got the fever? Where did you go? We need to find out the origins. When we find out the origins, then we will be able to pinpoint the exact problem, right at which we'll be able to implement a solution. So we need to find out what is the problem. Here itself, you don't need to write any, you don't need to read all these things at all. Within no time, I'm going to make it very clear. Let us understand. Let us enhance this. Let us enlarge this to the next level. What? Let us see. There are 20 cooperative processes. Otherwise, there are 10 cooperative processes. All these 10 cooperative processes will have a shared region in the main memory. Okay? It could be a database or a table or a data structure or anything. Understand carefully. These 10 processes, let us say this is first process. This is second process. When they execute a section of code, the shared memory will get accessed. The total process is just not limited to access the shared region, right? They do have a lot of other tasks to perform, in which a specific module in which when a process is executing, the shared region will get accessed. The shared region may be different. For a process P1, let us say the section of the code in which the shared region will get accessed is, let us say from 10th instruction to 20th instruction. For process P2, maybe from 15th instruction to 30th instruction. For process P3, they will be different. So what we need to do is, we need to make sure that only one process is in that specific section where the shared region is getting accessed. This is the section of code for this process 1. This is the section of code for process 2. Similarly, every cooperative process will have a specific section of code in which when it is executing, the shared memory region will get accessed. So what we need to do is, being a software developer, being an application program developer, we must make sure that whenever one process enters into that specific section where the shared region is being accessed, no other process is allowed to enter. Okay, so only one process, simple. In order to make it very simple, in order to keep it Rama got married to Sita, that one process should only be allowed to enter into the specific section of code in which we are calling it as a critical section. This is what the critical section. You don't need to read anything at all. So only one process is allowed. When one process already made its way to enter into the critical section, that means that the shared region is already being accessed. No other process should be allowed to enter into the critical section. So what we need to do is, we'll think only from one process perspective. Let us say there is a critical section. This critical section, this is totally critical section. It must be protected with 2 gates, gate 1 and gate 2. Gate 1, I will call it as an entry section. Gate 2, I will call it as an exit section. At the gate 1, any process, before it enters, it needs to seek the permission. Can I? If no other process already is in the critical section, this process is allowed to enter. Right after it is succeeded to enter, while it is going out, at the gate exit gate, it needs to admit that I am leaving the critical section. I am no more in my critical section. So none of you people need to wait. One more process can possibly enter into the critical section. Making that statement, I need to go out. So we need to provide a code for this. We need to provide a code of module for this in such a way that at the gate 1, every process that is before entering into the critical section seeks the permission. Right after it, upon successful entry into the critical section, sooner or later, any process will finish within the critical section, right after which it goes out. When it is coming out, it needs to make sure that I'm done. It admits that I'm done. Any process which want to enter, they can enter. Okay. So this is what, there are 2 gates. You can see general structure of a process PI. This process PI general structure has been protected. The critical section is protected with the entry section and exit section. Entry section for permission, exit section to say that I'm done with my critical section. Any process. When let us say one process is already in the critical section, all the other process will only be held at the entry section. I hope you got my very point. Okay. So what we need to do is, our solution to the critical section problem must satisfy all these criteria. Anybody can suggest your problem, suggest your solution for this critical section problem. Only thing is, we need to design these gates with a module of code. Entry section and exit section we need to design with a specific module of code. Our solution should guarantee these three criteria. First one is a mutual exclusion, second one is a progress, and the third one is a bounded waiting. You might have already heard, but one more time, let us comprehensively understand. Mutual exclusion is very simple. Only one process should be allowed to enter into the critical section. When one process is already in, no more process allowed. Progress is, let us say, no process is executing in its critical section, but one process wants to enter into the critical section. This process, without any delay, should be sent into the critical section. Let us say there are 15 people, along with me 16. None of us now in the critical section, but let us say Anu want to enter into the critical section. There are no competitors. Anu now should not be stopped at all. Nobody should dare to say no to Anu. Immediately you should enter. Got a point? So this is what the progress. Bounded waiting is, a person should not be allowed to repeatedly enter into the critical section. Let us say, looking at a priority, I am allowed to enter into the critical section, but any other process which want to enter, it will get stopped. Okay. Now I left the critical section, but scheduler decide to schedule me again. Exploiting the scheduling criterias, I cannot re-enter into the critical section because there are already some more processes are actually waiting to enter into the critical section. Okay. So any solution should satisfy all these criteria. In addition to which, when you propose a solution, you also need to make sure that operating system follows preemptive kernel approach or non-preemptive kernel approach. More about this preemptive kernel and non-preemptive kernel I am going to explain in the tomorrow's session. I hope you got it so far. What has been explained, and in tomorrow we are going to propose a few solutions to the critical section problem. That's it from the session. Any doubts, you can shoot it right now. Any doubts so far? Anu, or Tahir, or Tushar? Didn't have a mouse for this. Can I have this scrolled up? Okay, then that's it from the session. Any doubts? As tomorrow is the continuous session from this. We're going to continue the topic even in the tomorrow's session. Any doubts, whatever you have flashed in your mind, I just want you people to ask instantly in the tomorrow's session. So that's it for the day. Thank you so much. Anil Prasad Surampudi signing off. But before I leave, if anybody is there, I request you people to subscribe and share this session to as many people as possible, since to exploit this free sessions. Thank you so much. That's it from the session. Thank you so much. That's it.